Convection without phase change. What is convection? In most applications, heat is transferred from a fluid without phase change. Convection is when heat is transferred from a moving fluid to its surroundings. Convection amongst a fluid can take place naturally or can be forced through momentum transport. Natural convection occurs when the buoyant force, the force of gravity or the difference in density between fluids causes heat transfer to occur. Forced convection is when the fluid is forced to flow over a surface by using a pump or other equipment. Figure 1 shows an example of natural versus forced convection. Heat is applied to the bottom of a beaker full of fluid. The image on the left in Figure 1 shows how natural convection takes place due to the warmer fluid being on the bottom. Heating the fluid from the bottom causes the density of the fluid to decrease towards the bottom since heat causes the particles to separate. Since the warmer fluid is less dense, it will rise in the beaker, which causes natural heat transfer to the colder fluid towards the top of the beaker. This process continues until the fluid is at equal temperature throughout the beaker. Forced convection can be seen in the right image in Figure 1. A glass stir rod is used to mix the fluid within the beaker, which allows for heat transfer to occur more quickly. This is an example of applying force to a fluid for it to flow over a surface and cause heat transfer to occur. The temperature is more equal throughout the fluid for this example of forced convection as compared to the example of natural convection in Figure 1. Forced convection is an important topic in chemical engineering, especially when it comes down to designing heat exchangers. Heat exchangers are used in multiple different industries and are designed to be as efficient as possible, which is why it is important for chemical engineers to understand how forced convection works in heat transfer. Shell and tube style heat exchangers are the most popular amongst heat exchangers and are used widely across all industries because of their numerous advantages. These heat exchangers offer advantages such as easy maintenance and repair. They can be used in multiple different applications. They can handle high amounts of pressure. Figure 2 displays an image of the inside of a typical shell and tube heat exchanger. Two fluids flow throughout the exchanger and use convection to transfer heat from one to another. The fluid that is more likely to follow the walls flows through the tube side since it is easier to clean than the shell side. The number and length of the tubes and the number of times the fluid passes through the tubes is dependent on the situation. Turbulent heat flow is favored because of the increased mixing due to eddies created by the stream. Typically, a Reynolds number greater than 2100 is considered to be turbulent flow, but for the following equations, a Reynolds number greater than 6000 is preferred. The Dittus-Boelter equation is an empirical correlation for long tubes that have sharp-edged entrances and is used to calculate the surface coefficient of heat transfer for fluids. The Siedertate equation is also an empirical correlation used to calculate the surface coefficient of heat transfer for fluids in a pipe, but it accounts for conditions at the wall of the pipe. Because of this, the Siedertate equation is considered more accurate, especially for when the fluid temperature is much different than the temperature of the wall of the pipe. Water at atmospheric pressure in 25 degrees Celsius is flowing through the tube side of a 1-to-1 shell and tube heat exchanger. The water is flowing through a 2 cm diameter tube at 40 cm per second. The tube has an outer surface temperature of 100 degrees Celsius. If the tube is 10 feet long, find the convective heat transfer from the tube. The first step to solving this problem is finding the Reynolds number and determining whether the flow is laminar or turbulent. Viscosity and density of water can be found in the back of the textbook or online for these given conditions. To solve for Reynolds number, multiply the density of water by the velocity and the length of the pipe, then divide this value by viscosity of water. The Reynolds number for this problem is 89,978. Which means the flow is turbulent. The next step is to determine which equation to use to solve the problem. The Sider-Tate equation is the best option for this problem since it takes into account the conditions of the fluid near the wall. Step 3 involves finding unknown values in the Sider-Tate equation from Engineering Toolbox. The Prandtl number of water at 25 degrees Celsius is 0.613. And viscosity of the water near the pipe wall is 0.002814 g/cm times seconds. Now, we need to solve for phi. To do this, you must divide the viscosity of water at 25 degrees Celsius by the viscosity of water near the pipe wall and then put this value to the power of 0.14. Step 4 involves plugging values into the Sider-Tate equation to solve for the Nusselt number. Once the Nusselt number has been solved for, we can move on to step 5 where we will solve for Hi. To solve for Hi, the thermal conductivity of water at 25 degrees Celsius and 1 atm needs to be found first. This can be found on Engineering Toolbox and is equal to 0.6071 watts per meter times Kelvin. To solve for Hi, multiply the Nusselt number by thermal conductivity and then divide this value by the pipe diameter. Hi is found to equal 7068.72 watts per cubic meter times Kelvin. Now, the convective heat transfer coefficient can be easily solved for by multiplying Hi by the area of the pipe and the change in temperature from the wall of the pipe and the fluid. This is done in step 6, where we get a convective heat transfer coefficient of 101.587 kilowatts.